This video will introduce the general principles of sample preparation for powder X-ray diffraction. To begin, it is important to define, in a practical sense, the characteristics of an ideal powder X-ray diffraction sample. Note that the words practical and ideal are emphasized. In some cases, such as with the use of a flat sample, it is impractical to meet the theoretically exact conditions for sample shape. In other circumstances, it may not be possible to achieve all the criteria listed, as in the case of a sample with a smaller than ideal crystallite size. Lack of absolute confirmation to the listed characteristics does not preclude a sample from analysis under powder X-ray diffraction. However, the impacts of these deviations should be considered in the context of the desired analysis and compromises made, as necessary. For the parafocusing optics found in a typical powder X-ray diffractometer, the sample should exhibit the following characteristics. The surface should be smooth, flat, and positioned at the correct location within the diffractometer. Ideally, the crystallites composing the sample should be randomly oriented and within an optimal size range. The sample should be uniform and representatively measured, and finally, if possible, the sample should be infinitely thick and densely packed. Compromises will always be required in cases where sample size and/or quantity is limited, particle size or shape are not ideal, and sample presentation is limited, among other similar conditions. In the coming slides, each of these characteristics and how they impact powder X-ray diffraction measurements, as well as possible solutions to common problems, will be discussed. The first topic of discussion is the sample surface and its position. The top surface of the sample must be at the mechanical center of the goniometer. This is typically set by the interface between reference surfaces on the sample holder and diffractometer stage. Most often, the sample reference surface is the top portion of the sample holder. Since the interface between the sample and diffractometer reference surfaces determines the sample positioning, correct use of the sample holder and routine maintenance of the diffractometer are the primary means of avoiding sample positioning or displacement errors. Schematics of correctly and incorrectly prepared samples, shown here, illustrate how the incorrect use of the sample holder can result in sample displacement errors. Incorrect sample mounting is the most common source of displacement error. Errors in diffraction data due to sample displacement are common. Incorrect sample positioning results in shifted peak positions, distorted line profiles, and non-uniform irradiation of the sample, the magnitude of which increases with the amount of displacement error and changes non-linearly with the scattering angle. The figure above shows the impacts of both high and low sample displacement on the resulting powder X-ray diffraction data. Displacement error is typically one of the easiest issues to correct and should be as low as reasonably attainable. Significant errors can be observed with relatively small amounts of displacement. Height displacements greater than 100 microns, or approximately the thickness of a sheet of paper, can result in unacceptably large artifacts in the diffraction data. A closely related issue to sample displacement is that of sample surface geometry. The surface of the sample should be flat and smooth. Illustrations of common issues with sample surface quality are shown below. Errors resulting from distorted or rough samples include shadowing, particularly at low angles, resulting in poor and inconsistent sampling, as illustrated on the right. Additionally, errors similar to those caused by sample displacement, such as distorted line profiles and shifted peak positions, can occur to varying degrees depending on sample surface quality. Careful sample preparation is critical to eliminate these errors. Fine powders typically do not present any issues related to sample surface quality. However, in cases where the sample is composed of very coarse grains, particle size reduction may be a solution. In solid samples, planarization and/or polishing may be necessary. Crystallite orientation is a common and important consideration in powder X-ray diffraction. Only crystallographic planes which are oriented approximately parallel to the sample surface contribute to the diffraction pattern, as illustrated below. When no diffracting planes are oriented parallel to the sample surface, the crystallite will not contribute to the diffraction pattern. To sample all crystallographic planes with equal probability, the crystallites in the sample must be randomly oriented. Non-random orientation of crystallographic directions, known as texture or preferred orientation, results in some peaks exhibiting higher relative intensities while others are either absent or reduced. Texturing commonly occurs in powders when particles are anisotropic and specific crystallographic orientations are associated with the long or short dimension of the particle. The long dimension of the particle will orient parallel to the sample surface more often than a short dimension, resulting in oversampling or undersampling of certain planes. In this example, two collections of particles with a rectangular cross-section can be seen with their respective diffraction patterns shown above. Arrows perpendicular to the black and red crystallographic planes are shown for each grain and are collected next to each diffraction peak. When one of these arrows points upward within the range highlighted in green, the plane can contribute to the diffraction data. In the left-hand example, the orientations of the crystallographic planes are relatively random, leading to the same number of grains contributing to both diffraction peaks. The right-hand example, though, shows that most grains are oriented such that the long axis, and therefore the black planes, are approximately parallel to the sample surface. As a result, a disproportionately large number of black planes contribute to the diffraction data, whereas the red planes are almost all oriented such that they will not contribute to the diffraction data. The resultant diffractogram shows substantially stronger intensity for the peak associated with the black planes than the peaks associated with the red planes. In powder preparation, compaction, vibration, or settling can orient anisotropic particles. Texture is not only limited to powders, but can also occur in solids. This is most often the result of preferential crystallite growth and plastic deformation or working. Texturing in large, highly anisotropic particles may not be completely correctable. Potential solutions to texturing problems include the use of side fill or backfill methods for powder sample preparation. Slurry and front fill preparation methods tend to exacerbate texturing and should therefore be avoided. Loading the powder sample against a slightly roughened surface, such as frosted glass slides, can reduce the ability of particles to align against the surface. This feature is already present in many sample preparation tools. Careful sample loading practices, which avoid excessive vibration, manipulation, overcompaction, or smearing in powder samples, are strongly recommended. Size reduction techniques, such as milling, may help in some circumstances by reducing particle size and aspect ratio, provided that the milling process does not alter or contaminate samples. Finally, the use of mixing aids, such as powdered cork, can disrupt ordering in powders that are highly prone to texturing, but may also introduce unwanted background. Crystallite size plays an important role in sampling, resolution, and pattern reproducibility. In powder X-ray diffraction, only a small percentage of crystallites in a sample contribute to the diffraction pattern for any given diffraction line. Larger crystallites in the tens of microns or higher produce sharp diffraction lines but have relatively few crystallites contributing to the diffraction pattern. This results in good resolution but poor intensity reproducibility. Smaller submicron crystallites produce broader and typically weaker diffraction lines, which reduce the ability to resolve closely spaced peaks. However, intensity reproducibility is generally good due to the relatively large number of crystallites contributing to the diffraction pattern. The optimum crystallite size range for powder X-ray diffraction is in the 1 to 10 micron range, where narrow diffraction lines are possible while still maintaining a sufficiently large number of crystallites to contribute to the diffraction pattern. This results in both high resolution and high intensity with good reproducibility. It is important to note that grain or crystallite size is not always the same as particle size, as an individual particle can be composed of multiple discrete crystallites. Optimization of the crystallite size may not be correctable in many cases, especially when crystallite size is small or sample manipulation is not possible. Particle size reduction methods, such as milling, can be used to reduce the crystallite size when appropriate. The following example illustrates the impact of particle size on sampling statistics and intensity reproducibility. The example on the right shows a collection of particles much larger in size than those observed on the left, resulting in a significantly lower number of particles contributing to the diffraction pattern. In the left-hand example, due to the large number of particles present in the sample, both the black and red planes contribute equally to their respective diffraction lines. However, in the right-hand example, the relatively small number of particles present in the sample results in the red planes, by random chance, not being aligned to contribute to the diffraction pattern. This results in no measurable intensity associated with the red crystallographic planes. If this coarse-grained sample was prepared repeatedly, the line intensities would vary each time by random chance, whereas the finer-grained sample would not exhibit the same level of intensity variability. The transparency of a sample to the X-ray beam is an important factor in sample preparation and sample holder selection. Sample transparency is an intrinsic property to the sample material which cannot be changed. In general, the impacts of sample transparency are only addressed through modifications in sample preparation or presentation. Samples should be infinitely thick, uniform, and densely packed such that the beam only interacts with and generates data from the sample itself. The penetration depth of the beam decreases with increased sample material density, sample absorbance, and packing density in the case of powder samples. Additionally, the penetration depth will decrease with a reduction in incident angle. Illustrations of typical interaction volumes are shown on the right at both lower and higher angles. As the incident angle increases, the beam penetrates deeper into the sample, while the projected area on the sample surface grows smaller. As a result, the sample volume remains constant over the entire scan range. However, the data being collected originates from different parts of the sample at different points within the scan. When sample thickness is insufficient, intensity errors, which vary with angle, can occur, and the assumption that the interaction volume is approximately constant is no longer valid. Additionally, a signal from the substrate or sample holder may be present in the diffraction data. This is illustrated in the schematics below. In the higher density sample to the left, the beam remains entirely within the sample. However, the lower density sample on the right allows the beam to interact with the sample holder. Infinite thickness varies from the micron to submicron range for dense and strongly absorbing materials, up to the hundreds of microns for light materials at the wavelengths typically used in laboratory X-ray diffraction instruments. To limit unnecessary beam penetration, powder samples should be packed as densely as possible without inducing other artifacts. In most cases, use of a thick sample is recommended when possible to prevent interactions with the substrate or sample holder. Samples exhibiting relatively high transparency may require special treatment to reduce measurement artifacts. Thick, highly transparent samples can generate artifacts similar to displacement errors, such as shifted peak positions and distorted line profiles. Thinner samples will reduce these issues. However, due to the transparent nature of the sample, the beam will interact with the underlying sample holder. Thus, in this case, the use of a zero background plate is recommended. Other, more advanced techniques for addressing highly transparent samples exist but will not be discussed in this presentation. Opaque samples generally do not benefit from special sample preparation solutions. However, some issues with these samples should be considered. Dense and/or strongly absorbing materials reduce the number of crystallites sampled, which results in lower intensity and in some cases poor particle statistics. Strongly absorbing samples may also generate significant fluorescence, which contributes to a high background. Like sample transparency, the irradiated area is an important consideration in sample holder selection and instrument configuration. As illustrated on the left and in previous slides, the irradiated length increases as the incident angle decreases and is determined by a combination of the divergent slit and the incident angle. The beam width, on the other hand, remains constant and is set by the mask. As in the case of excessive beam penetration, over-irradiation of the sample can generate intensity errors which vary with angle. The assumption that the interaction volume is constant is no longer valid, and a signal from the substrate or sample holder may be present in the diffraction data. Over-irradiation of the sample can be prevented by either ensuring that the selected sample holder is large enough to accommodate the selected scan range and diffractometer configuration, or ensuring that the diffractometer settings match the necessary sample holder. Size reduction has been discussed as a potential solution for several of the challenges previously noted, and is an important tool in the preparation of powder X-ray diffraction samples. Particle size reduction can be beneficial in powder X-ray diffraction by optimizing particle and/or crystallite size, thus homogenizing the sample, and in some cases reducing the potential for texturing. However, grinding techniques can also cause the following problems. They can change the sample by causing the amorphization of crystalline material, causing reactions, or inducing phase changes, particularly in soft or ductile materials. They can contaminate the sample from milling media or milling containers, and they can induce stress and/or defects into the material. The two most common methods of size reduction include the mortar and pestle for manual preparation, or various types of mills, which are generally powered externally and are higher energy methods. The mortar and pestle is a convenient means to pulverize smaller samples of softer materials. However, for most materials, particularly harder materials, mills produce a more uniform and higher quality result. In addition, they can produce a much finer particle size. If beneficial or necessary, optimum grinding conditions such as time, energy, method, and media should be determined experimentally for each sample type. The following two examples illustrate how grinding conditions impact X-ray diffraction data. The left example shows the effects of different milling times on a cement sample. Substantial changes in the intensity of the diffraction line associated with gypsum can be seen with increased milling time, while the line associated with the C4AF remains unchanged. In the right example, continuous changes in the intensity and line width of the calcium silicate phase can be seen with increased milling time. This concludes the introduction to the general principles of sample preparation for powder X-ray diffraction. The following table outlines the various sample holders supplied by Malvern Panalytical, along with their primary applications for powders and solids, as well as the required sample size and pertinent holder dimensions. The video can be paused at this point to review the table. Details of each sample holder, along with examples and guidance for use, will be addressed in the individual videos for each holder type. This concludes the introduction to the general principles for the preparation of powder X-ray diffraction samples. For more information or to contact us directly, please visit our website at www.malvernpanalytical.com.